Alright, so this is going to be the video lecture for chapter 21. We talk about analog to digital conversion. So let's look at our objectives. We have here, we're going to provide some examples of analog and digital communication systems. We want to look at some advantages of digital. And then we're going to talk about the basic steps of analog to digital conversion, sampling and quantizing and encoding. Give examples of analog waveforms, sample rates, and resolution. We want you then to be able to determine the resulting quantized signal and the binary encoded analog to digital outputs. Whenever you see this A/D, it means analog to digital. I want you to calculate the Nyquist sampling rate for an analog signal, and then given the number of bits of an analog to digital process and sampling frequency, determine the generated bit rate. And then they want you to define the quantization error and state the only way to improve it. So think back to chapter 19 where we showed you guys in the security exercise the waveform for voice, and how that we know that voice is an analog signal and it doesn't have discrete values, it has continuous values. Each one of those is continuously changing and having an infinite number of possible values between its maximum and minimum values. So this being an analog signal that we have here, see our maximum, our minimum, and any one of those is a possible value. There's no set values, so it would only be here or there or there. Instead, it can range anywhere in those areas. So what we're talking about is how we can translate from these continuous values to discrete values represented by ones and zeros in some way, shape, or form. So let's give some examples of analog systems. So in the past, especially when I was growing up, we had things like cassette tapes and VCR, VHS, which was used with VCR. And all those were information encoded in magnetic tape, which is read via analog system. And some of you may have seen these. Some of you may, in fact, actually own them. But I'm assuming that majority of you grew up with CDs, DVDs, that type of information. And that's what it progressed to into my teen and my early adult years. But as time has gone by, we've actually got even more progressive, and we've been able to store data more efficiently and not have to worry about even maintaining physical copies like CDs or VCR or VHS tapes. And all that stuff is streamed or stored in a digital format, whether it's music on Spotify or Pandora or some sort of Amazon, Google platform, or videos such as your iTunes movies or an Amazon Prime, and then obviously the ever popular Netflix. All these things are now stored in a digital format, even though they represent a lot of analog information from pictures to sound. So when we talk about digital systems, we're talking about any system that uses discrete electrical signals to store or transfer information. And we've talked about this in the past where we said, hey, they're going to use discrete voltage levels. And you can see here on the right-hand side, then we have a discrete voltage level there and a discrete voltage level there in pulses. And so we would have a 0 for a low pulse and a 1 for a high pulse. But on this bottom graph, we actually have this two different levels, but it's shown by a frequency. It's constantly oscillating back and forth. But when it oscillates with a certain amplitude, it represents a 1, and it oscillates with a separate amplitude, it represents a 0. So in both of these situations, we're seeing that it has that discrete electrical signals. And we're typically going to represent this in binary. And that's what it means to have a digital signal system. So digital signal advantages. So one of the most important advantage of digital signals is they're relatively immune to noise. So if we remember our constant continuous values, right, in an analog signal, and we see these small bits of noise in the signal, it can be garbled if we're translating that directly. So we're going to hear that noise in that signal. However, when we're dealing with a digital system over here, we only have two values. We either have a 0 or a 1. So when we have this 1 and this 0, and the system gets these noise patches, the system has to say, hey, I see that noise, but I'm either going to be a 1 or a 0. So it will then constrain that value and interpret it as a 0. And here, it's going to say that's got to be a 1, even though there's noise around there, because it's constrained. It's only looking for one of two values, 1 or 0. So the noise can be large enough. If there's significant noise, it can cause a misrepresentation. So for example, if the noise in this area was shooting up like this, it could feasibly cause the system to believe that this is supposed to be a 1. And that does happen, and there are systems out there that, or processes out there to correct things like that. So the other thing that goes with digital systems is if we had a long haul transmission and we had a transmitter down here, and it was transmitting wherever it's going along this wire, and then we have this receiver, which is a long ways away. If we know that there can be a lot of noise on this line somewhere, what we can do is we can actually just break it, and we can actually put a receiver in the middle that will receive it, interpret it, take that information, and then clean it up, and then send it back out. So it receives it with all the noise in it, cleans it out, so that it can say, hey, it's supposed to be a 1 or a 0, turns it back into those 1s and 0s, and then sends it back out on the other side cleaned out. So let's just annotate on here that there would be noise, and then it gets cleaned, and then there would be some more noise again, but not enough noise to destroy or corrupt the signal. So instead of having a potentially corrupted signal at the receiving end, we end up getting a clean signal. Other advantages are error detection and correction. So we have digital signals processing techniques that allow us to not only detect errors but correct them as well. So this incorporates filters and then error correction processes. And it's not just the checksums that you guys may remember from some of the security exercises that we did. Actual processes to correct bit errors themselves. And we're not going to get into that. It's just good to know that those things exist out there. So easier multiplexing. So here it talks about allowing multiple signals to share a transmission channel. So I want you to think about radios. When you're on a long car trip across the country, for example, and you're moving from one location to a next, and FM 95.7 starts being overridden by another FM 95.7 from a different county or even a different portion of that state that you're traveling through, and they step on each other. When you're thinking about that, I want you to think like, so this is a counter example for analog. But if we're talking about the digital systems, think about how many people use an internet network. Or on your Wi-Fi at any one time. So that can be just an example of in your real life how those things take place and are experienced. So easier to process and store. So I went and looked this up. So the complete works of Shakespeare, William Shakespeare, right? You go out and you can go to Barnes & Noble and you can buy this book over here, 1,280 pages. Costs about $30. Or you can go to the Gutenberg Project and you can find plain text copy of that same information and more, and it's free. 5.6 megabytes worth of data. And the issue there is that we could go buy this flash drive, 16 gigabytes, and this costs about $10. So I can spend $10 and store roughly 3,000 copies of the complete works of Shakespeare, or I can pay $30 and it takes up 1,280 pages in the space on my bookshelf. One I can carry in my pocket, the other I cannot. So as time has continued to go on and we continue to get better and better transistors and better power systems and data transmission, we have better ability to store things digitally. In fact, it's one of the reasons we can actually hold this course in the way that we're holding it now, is because our digital systems are so improved. Okay, so we've talked about some advantages of analog systems, and we've talked about all those different things so far. But what we're going to start talking about, and what we're going to talk about for the rest of the lecture, is conversions from analog to digital and how we do that. So there's 3 major steps, and we're going to talk about them each sequentially. So there's sampling, how we're going to get that information and sample the analog signal so that we have an accurate representation when we get to the digital side. And then we talk about quantizing and encoding. And quantizing and encoding are going to be how we represent that information in a digital format. So I'm actually going to stop this video now, and then you can roll right into the next one as soon as you're ready to come back to it. All right, so welcome back, and let's move on. So we're talking about the analogs to digital conversion, the sampling portion. So this is the process of measuring the voltage of a signal, an analog signal, at regular time intervals in order to recreate it later on. So our goal here, and this is going to be one of the things I want you to pay attention to throughout the rest of this, is our goal is to get an accurate representation of the signal. And so we're going to stop and we're going to kind of focus on this plot for a second. And what I want you to notice is, one, we have T sub s here. And this is our sample period. And this is going to be at regular defined intervals, as we've already talked about with period. But this is a period that's actually faster than the period of our overall signal. So if we were to think of this analog signal as potentially having a period from here to here, right? Because of it completes a cycle, even though it's not a regular cycle. This period is much larger in comparison than our sample period. This is going to be important. We'll talk about that in a little while. But then we also see a sample frequency down here, denoted as F sub s. And make sure that you are aware of that T sub s is your sample period and F sub s is your sample frequency. So if we're remembering our goals to getting that accurate representation of the signal, and we've talked about T sub s has to be much faster than the period of the overall analog signal, that allows us to know a couple things. First off, so more samples, more accurate. And you can see that because where each one of these dots are, when we're doing this digitally, we're basically playing connect the dots. So if we're connecting these dots, the more dots we have in between, the better that overall representation is going to be. You're going to see here, for example, we cut off the tip of that crest. But if we had a dot in the middle, it would cut off less of it. So the more of those samples you have, the more accurate our recreated signal is going to be. And we're not actually going to be able to connect those dots precisely like that. And we'll cover those things later. But when we come down to this, number one, more samples, more accurate. And number two, this is kind of a rule. This is a hard and fast rule that we can't violate. We actually have to have a sample rate. So our sample rate must be faster than the what's called Nyquist sampling rate. And this is going to be F sub capital N. And this is based on the work of a scientist, an engineer a while ago. And F sub N is equal to 2 times F sub max. And F max here, that is the maximum frequency in our analog signal. And so when we're all through with that, we end up with having this F sub S, our sampling frequency, must be greater than F sub capital N, where F sub capital N is equal to 2 times F sub max. So with that, let's go ahead and move forward and look at an example. So here we have a signal. It's got a 1 hertz frequency. We have 1 cycle per second. Thus, t equals 1 second. From that, 1 over 1 equals 1 hertz. That'd be seconds. So we have a 1 hertz signal. And we have several examples of how this has been sampled. So let's start in the bottom left. And we have a starting sample and then a sample every 0.5 seconds because we have a sampling frequency of 2 hertz. So our period, our sampling period, T sub S equals 1 over 2 hertz. That equals 0.5. Change out the size of this pen. So when we have this, we see we have a sample there, so on and so forth. And if we were to recreate this, we're going to talk how that's going to get done later, but we can see that if we connect these dots, assuming that it's a sinusoid, we're going to be able to connect these dots well enough that we can recreate this signal. Now there's highs and lows there. Then if you look at this over here, 1.5 hertz, we'll go ahead and convert that. So T sub S equals 1 over 1.5 hertz. That is going to equal 2/3 seconds. So we see this here. This is sampled there, again at the beginning, and there. Now, if we were to actually start connecting this, assuming it was a sinusoid again, and we see we have a high here, we've got this there, down there, we would actually start to see something that looks like this. And what this does is it actually changes the way our frequency from our actual signal looks. And if we look at this signal has a period that goes from there to there, and we would say that that period is actually, what is that, 2 seconds? So t there equals 2 seconds. So then our frequency is going to be 1/2. So now we actually have a lower frequency than what we had originally had. So this is the problem with Nyquist, with not meeting this Nyquist sampling rate rule, is you start having lower frequencies show up in your signals when you try to recreate them. And we can see down here in the lower right hand corner that because we have a 3 hertz sampling rate, we are actually able to accurately classify that signal, and we don't have any funny business showing up. Okay, so here we have a practice problem. They want us to consider the signal from an oboe that's depicted below, and they have the time domain and the frequency domain. And then based upon, they want to see out what is the maximum frequency represented in the oboe signal. We can use the frequency domain to grab that. And then they want us to figure out what's the sampling rate that must be exceeded in order to accurately reconstruct this signal from its samples. So what I want you to do is pause it, use the information that we've talked about thus far, and go ahead and work that, and then come back, and then we'll go through it together. Okay, so assuming you've went through it and you should have some sort of information already, but let's go ahead and look at this. So first off, we're asked what the maximum frequency present in the elbow signal. And if we come over here to this portion of the frequency plot, we can see we have a plot right there. And we can estimate that and say that's probably, let's call it 5,700 hertz. So F max equals 5,700 hertz. And if we go ahead and we can move on to what is the sampling rate that must be exceeded, we know that F sub S must be greater than F sub capital N, where F sub capital N equals 2 times F max. All right, this is just some straightforward math. F sub N is going to be 1100 or 11,400 hertz. So then F sub S must be greater than 11,400 hertz. You could also write that as 11.4 kilohertz. Okay, so at this point, I'm actually going to stop this video, and you guys can take a break. Come back when you're ready for the next one. All right, so now that we've been able to figure out how we're going to get the samples of our data, now what we're going to do is we're going to start working on what's called quantizing and encoding. And this is the process of mapping our sample voltages to discrete voltage levels. So when we do this, we're looking at discrete voltage levels represented by binary numbers. And we worked with binary a lot of it thus far in the course. And one of the things that we're going to run into an issue with is we know that we have an infinite number of values for our analog signals. However, we only have a finite number of representations with our binary numbers. Unless we had an infinite number of bits, which we know to be impossible, we have to restrict our values to certain finite levels. And this is called quantization or quantizing. And this is where we're going to have some issues in how accurately we can portray signals later on, and we'll talk about that towards the end of this lecture. So we're going to go over some quantization levels, and we're going to move forward talking about this information. So the analog to digital systems are characterized by the number of bits. The number of bits they have is going to be a very important bit of information. And what we're going to do is we're going to say that we have an n-bit system. And an n-bit system is going to have a certain number of quantization levels. And we find that by saying it actually has 2 raised to the n quantization levels. Quantization levels. And each one of those is going to have a resolution Q. And Q equals the maximum voltage minus the minimum voltage, all divided by 2 raised to the n. So we're actually going to get into looking at an example on how to break this down. But before we go down to the example, we're already going to say right now that our example has 3 bits. It is a 3-bit system. And before we go on to it, let's go ahead and break down what Q is. So Q equals Vmax, and Vmax here is going to be 1 volt, minus, and the minimum is going to be negative 1 volt. So all over 2 raised to the 3. So we do our math here, we end up with a 2 in the numerator and an 8 in the denominator, and we end up with this being 0.25, and probably should carry those units over. So 0.25 volts is going to be our quantization levels. So let's look at that example. So what we've already done here is we've already broken this down into 8 different levels. Each one of those already separated by 0.25 volts. And we can use this to determine the bit sequence for our samples. The way we're going to do that is we're going to label our ranges, and I'm going to go ahead and label those now. We're going to start at the bottom at 0, 0, 0. Remember, 3 bits, and then we're going to work our way up. So now that we have that, we can actually start labeling out this bit sequence, starting with our first sample. And I'm going to color code these a little bit so we can keep things organized. Okay, so I'm going to work these first three for you so you can see how it's done, and it's fairly straightforward. So I'll do our first bit, our first sample, sorry, our second sample, our third sample, and now I'm going to go ahead and let you complete this. So pause this before you continue on, complete the bit sequence, and then we're going to get onto this next portion in just a short bit. Okay, so this should be what you should have ended up with. You should end up with, sorry, let me undo that. So it should have been the green samples here, and then the samples in pink or magenta right there. And we see that this is actually, that's quite a few bits, right? That is 13 times 3, that's 39 bits. And how quickly does it do that? So that's 39 bits. And how fast does it do that? Like, what's the sample rate? Let's double check that again. So we had a sample rate here of 0.5 milliseconds. So 0.5 milliseconds. So 0.5 milliseconds equals T sub s. So then we then can say that F sub s equals, that's 2000 hertz. That's a pretty fast sampling rate. And what we're going to be able to do is, using our sample rate and our bit depth, we're actually going to be able to get what's called our bit rate. And bit rate is written R sub B, and it's going to be something we're going to be asking you to calculate quite a bit through here. So you're going to write this equation down, and it's going to be N, our number of bits, times F sub S. So this is N equals bit, what's called bit depth. And that is the number of bits we use to represent a sample. In this case, it's 3. And then F sub S is our, just write it down again, that's our sample frequency. All right, so for our example, we have, let me get blue, R sub B equals 3 bits per sample times 2000 samples per second. So our samples here are going to cancel, and we're going to be left with 6,000 bits per second. And we've seen this before, abbreviated as 6,000 BPS, or we could also write it as 6K BPS, because kilo just means 1,000. So we're going to take this, we're going to go over to a practice problem. So here we have this analog waveform, looks like that. And what we're being asked to do is see, we have a sample rate of 500 hertz, 2-bit quantizer, and an input range of -1 to 1 volt. And it wants us to circle our sample points, indicate the quantization intervals in the corresponding digital words, indicate our digital word assigned to each sample point, and then what is the stream of binary bits generated. So what does that overall binary bits look like? And then what is the resulting bit rate from this analog to digital converter? So go ahead and pause the video, work through those questions, and then when you're all done, come back and we can work through it. Okay, so for A, one of the things that we want to be able to do is figure out where those sample points are going to take place at. And we know that our first one takes place right there at time 0, but to find the next ones, we actually want to find our sampling period, and we have our sampling frequency, so we have F sub S equals 500 hertz, which then allows us to find T sub S, because that just equals the reciprocal, and that equals, I believe that's 2 milliseconds. So now that we have that, we can go check our horizontal axis there. We're in milliseconds, so now we can just circle all of our sample points just by going out every 2 milliseconds and circling that. And there we go. Then we're going to go ahead and indicate our quantization intervals. So our quantization intervals, we have 2 bits, So we have to find our overall resolution, so Q. So we have Q is going to equal Vmax minus Vmin. So that's going to be 1 minus -1 over 2 raised to the 2. So then we have 2 over 4 equals 0.5. So with that, we're able to start marking out our individual quantization intervals. That is right there. This is there, there, and here. So now we can start from the bottom. We can label out those binary words. I say words, I use quote-unquote words. 0, 0, 0, 1, 1, 0, and 1, 1. So from there, we're going to be able to move on to part C. So back to blue, indicate the digital word assigned to each point. So if we have this one here, we actually know that we are kind of in between, but let's assume that it's actually, this is a 1, 0. So we're going to say that's a 1, 0. This one here is a 1, 1. And we have another 1, 1. This is a 1, 0. Come down here, we have a 0, 0. And this one here is a 0, 1. So moving on to part D, we can actually then start writing those out. So D, we're going to get 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1. Just underlining those to keep those distinct from one another. And then for part E, we can start working that. And that will be what is resulting bit rate from A to D conversion. And we can see that we just need to say R sub B equals N times F sub S. And here we get that to be 2 times 500. And that's going to be 1,000 bits per second. So with that, you should be able to pause it or end this video, and we'll be able to roll into one more video, I believe, after this. All right. All right, so we've sampled and we've quantized and encoded the signal. And we now have a binary representation of what that looks like. And we can actually, from that, generate a digital voltage waveform that looks a lot like this. And you should remember this from chapter 12 when we talked about the physical layer. And we're able to either ready to transmit it or ready to store it. And this is really useful in wired medium, but it's not really useful in wireless medium. So we actually have to discuss that a little bit later in digital modulation. It's not subject to this lecture. But before we can ever get to any discussing any of that stuff, we're actually going to discuss how we convert back from digital to analog. Because I know that many of you are sitting there watching this or listening to it, and it's going from a digital form to an analog form, and it's probably relevant to discuss how that happens. So if we take into consideration the example that we've used in the past, where we had that analog signal, and we've already converted it to digital, and we have this digital bit sequence down here. So what we're going to do is we're actually going to take that, and we're going to convert, and we're going to represent that in the digital scheme. So each one of these tick marks along the bottom is going to represent when one of our samples is going to stop. And we're going to end up getting, so we're going to start, and we'll start in the middle here of each one of these, and it'll just go out as far as that sequence goes. And then we'll go to the next one, and we'll say, okay, that one lasts that long. And then 1, 0, 0, and then 0, 1, 1, 0, 1, 1. Start marking these off so I can keep track of where I am. And then 1, 0, 0. And then that goes all the way up to 1, 1, 0. So come up here, followed by another one. And then 1, 0, 0. 0, 1, 0. So that's all the way down here. There. And then all the way down to 0, 0, 0. So that is right about there. 0, 0, 0. And then 0, 0, 1. We do that. So now I'm just going to do some connections so we are moving through those We have one continuous signal jumping in between those voltage levels, obviously. So this is what that is going to look like. It's going to look more boxy, more like a set of staircases. That's not a very nice set of staircases. And this is going to be what's going to happen. We're going to have that bit sequence here. We'll all go through a digital to analog converter, and we're going to end up getting these quantized levels held for samples for the duration of the sampling time. So this is what it's going to look like, and let's actually go and overlay this against the original signal. So if we look at it overlaid, we can see that it matches the overall analog signal, but we have distinct differences, and in some places the differences are worse than others. So right here, that's not a very bad difference at all. However, here, for example, that gets to be a pretty big difference, or in this case, that's an even larger difference. So this is actually going to be the next topic that we're going to discuss, and it's called quantization error or quantization noise. And quantization error or noise is that small difference between the original analog signal and our digital to analog signal that's been recreated, or I'll say quote unquote reconstructed. So it's that rebuilt signal and the small difference between those two things. And you can see in this example we have here at the bottom of the page, we have a 3-bit analog to digital conversion, and we end up having what is approximately 0.05 plus or minus volts in error. So that noise is of a certain size, and that noise, if it's too great, will end up starting to characterize as static on a line. So if it was an audio signal, you'd have static and you'd be able to hear it. So the ways that we actually go about correcting this is by increasing the bit rate. You need more bits to give better resolution so that we can better match that signal. And in this situation here, we see that we have 4 bits, and those 4 bits allow us to get a better approximation to that. One of the other things, so we say I already introduced more bits is more accurate. But one of the other things we want to think about is if we had more samples. So more bits is going to be your key, but more samples is also going to give us more accuracy as well. So with those, you can see that down towards the bottom we have that another error plot, and we have much less. We have about half as much error as we did in the first plot with 3 bits. So more bits does decrease our overall noise, our quantization noise in that reconstruction. And if you have any other questions or concerns regarding what's been taught, please let me know in the forums via email. Email is obviously one of your guys' favorite ways to get a hold of me. Please use it, and I'll be available in the live EI sessions as well. So I hope you're doing well. Take care of yourselves, and until next time.